50,000 feet up, meaning that it's very abstract and there won't really be any formulas or any kind of problem solving that you need to take away from this. More, I'm setting the stage for just how important conservation laws are and just how cool physics is. And so I want to talk to you about a few kind of underlying um, truths that physics reveals about our universe that you don't usually get to talk about in a first year physics class. And in fact, it's probably maybe a little inappropriate for me to talk about it and may go over your heads here, but it's something I think about a lot and one of the features that really attracts me to physics. So there's this problem in science that, we develop all these laws and rules and theories and stuff, and they tend to be domain specific. So like, for instance, um, we say force equals mass times acceleration, right? So that makes sense if you have an object that has a well-defined mass and you have well-defined forces and stuff. But what if you're talking about like individual protons inside the nucleus of an atom? Does it really make sense to talk about forces then? Can you explain how light works and operates when light itself doesn't have any intrinsic mass? So there are limits to even really general theorems like F equals ma, which is a foundational kind of physics formula. And so then the question is, and this is a fair question, is are there any sort of physics principles or scientific principles that operate at all scales, for the entire universe and down inside of an atom and in our everyday lives? And the answer is there are, and they are the conservation laws. There's just a handful of them, and I'm going to talk about a few of them in today's lecture, and we're going to go in depth on two of them in this course. And they'll get their own kind of like rollout and problem solving and chapters in the book and stuff. But for today, I just kind of want to give you an overview of these conservation laws. According to Richard Feynman, there's about 6 of them total, and I'm just going to mention 3 or 4 of them here today. They get the last 2 are increasingly abstract. So what are they? So here are the 3 that we traditionally spend a lot of time in a first year physics class. They're linear momentum, that is your inertia in motion, right? So your inertia is measured by your mass, and your motion is measured by velocity. And so your linear momentum is a product of your mass and your velocity. There's an angular version of that, right? You can also take your mass and you can spin it. And you should already know by like spinning tops and things like that, that's also a quantity that's conserved, right? So that's your mass in a rotation motion. And that turns out to be a conserved quantity also and explains a lot of physical phenomena that you see. And then energy, right, which is something everyone talks about and hardly anybody understands. But energy basically is a measure of your ability to affect change in your environment of any kind. And that is also a conserved quantity, right? And so these 3 things, along with the other 3 or so conserved quantities, are the only known laws of science that are true at every kind of level and every kind of scale that you can think of. If you like, they are the drivers for all of other science. So what does it mean to be a conserved quantity, right? So let's define that. If you have an isolated system, that is, things are left to their own devices in a room or something like that, and there aren't any outside forces and nothing's coming into the room or leaving the room, then you could consider that an isolated system. And although the things in the room can interact with each other and exchange mass or whatever, do whatever they want in the room, if they are truly isolated, then what are the things that you could come back and measure 5 days later or 2 minutes later or go back in time like 3 weeks earlier, and as long as it was isolated, what would be the things that wouldn't change about it, right? And that's what a conserved quantity is. Conserved means it's the same over time, right? It's unchanging. And so why does the universe conserve these quantities? And surprisingly, this is a question that has been answered. Right? We know the answer to this, and it's thanks to a very under-celebrated, although she's coming into her own now, some 100 years later, but Amy Noether, an early 20th century physicist, praised by Einstein for her work. But as a Jewish woman physicist in the early part of the 20th century, she was kind of sidelined. But now there are books that are being written by her, and she's becoming part of the canon. She actually proved mathematically why certain quantities are conserved, and the reason that certain quantities are conserved in physics is because there are certain symmetries in the universe itself. So for example, for the main three here, let's just walk through these. Why would a quantity called linear momentum be conserved? Why is it that your mass times your velocity is an unchanging quantity? And the answer is that she proved that it's because we live in a universe where the laws of physics are the same at different locations, right? So if we conduct experiments inside a room on Mars or on Earth or in Tokyo or in Washington, D.C., we expect to find the same relationships between quantities, when we're doing science. And the fact that the laws of the universe don't change from location to location is a symmetry that's embedded in our universe. And if that symmetry exists, then there is a conserved quantity called linear momentum. That's what she proved. The angular momentum is very similar, right? So why is it that once you get inertia spinning, it will continue to spin until acted on by an outside force? And that's because if I face north and do my laws of physics, or I face south and I do my experiments, or I face east, or anywhere in the universe, it's directionally independent, right? So the laws of physics are the same in different directions, and that's a symmetry, a different kind of symmetry than location, right? It's orientation, and because the laws of the universe are orientation independent, that's a symmetry that's embedded, and that implies a conserved quantity of angular momentum. And conservation of energy, the most abstract maybe of the three conservation laws we're talking about here, that comes from a symmetry that is so subtle that hardly anyone ever questions it. But it's that the laws of physics aren't changing over time. F equals ma yesterday, it's going to equal F equals ma is going to be the relationship between force, mass, and acceleration tomorrow as it is today. And so the fact that we live in a universe that is unchanging in time, as far as the scientific relationships that we uncover, that is a symmetry, also symmetry over time, and that implies a conserved quantity, which is called energy. So linear momentum, like I said, we're going to spend a whole unit on this, right? But what is a way of thinking about that is that you can have within the room, say your isolated system, you can have objects collide with each other, right? And so one object's velocity may decrease when it hits another, but the other object's velocity will increase such that the mass times the velocity of the total of all the objects in the room is the exact same number before and after all of the collisions, right? Here's the formula for it, right? It's mass times velocity. Velocity is a vector, so momentum, traditionally identified with the letter P, is also a vector. So this is a conservation law of a vector quantity, which means the direction is also conserved, right? And so you would technically find it for a whole system by just adding up all the individual momenta of all the individual objects in the room. And it is that total that is conserved. So angular momentum is very similar, except that it involves rotation. So the quantities, the descriptions that are involved in angular momentum are a little bit more abstract, right? So we don't talk about distance in meters, we talk about angle in radians, and we don't talk about velocities in meters per second, but we talk about angular velocities, which is radians per second. And we don't talk about forces being exchanged when they collide, we talk about torques, right? Torques is like the angular equivalent of forces. It's actually technically it's the force that causes you to rotate, right? And so similar to mass times velocity, angular momentum is something called your rotational inertia, which is slightly more complicated than your mass. And honestly, I don't know that we're going to get to this unit this year. This may be one of the COVID sacrifices that we have to do in the curriculum. The I here stands for something called rotational inertia or angular inertia, and it's a product of your mass and where all the mass is located, right? If you pack yourself very tightly, you're easier to rotate than if you spread your arms and legs wide. So obviously the ability to rotate you is not just a function of your mass, but it's mass and how it's distributed. And the omega here is just angular velocity, right? So that's radians per second. But otherwise, the idea of it is the same as linear momentum. Right, and so then we have the energy, and when you isolate the energy of a system, then you can't be allowing any temperature, heat can't be flowing in there, nobody can do any work, and there are three forms of energy, although this really reduces to two. So the three forms of energy traditionally that people talk about are the energy of motion, which is kinetic energy, the energy of position, right? You can have a relationship with another object, sort of be gravitationally attracted to it, or electrically charged, repelled, or attracted to it. And because you have that relationship and you're exchanging forces, there's some potential energy between the two objects because of their relative positions. And then here's the third one that's kind of a fake, but that is inside of an object, right? There are individual molecules and atoms and stuff like that. And so they are storing their own flavors of microscopic kinetic and potential energy. And instead of dealing with the billions and billions of individual atoms having their own Ke and their own Pe, we call those things like temperature and the energies required to undergo phase changes and all that kind of stuff. We just bundle all that stuff together and say it's all internal energy. But really, if you were to take out a microscope and dive down in there and look at the individual particles inside of an object, you would say, oh, yeah, it's just kinetic and potential energies, multiplied over billions and billions of objects, right? So just like friction and normal force is like too complicated to model as electrons repelling other electrons, that's kind of what we're doing with thermal energy here, is we're bundling all that stuff together. So anyway, when we talk about the total energy being conserved, it's really the sum of all of these kinetic and potential energies inside the room. And so when we say they're conserved, we mean that after some time, as long as it's isolated, the initial momentum is equal to the final momentum. That's linear momentum. And the same is true for angular momentum, and the same is true for energy. Notice that the two momenta are vectors, and so direction matters. And energy is a scalar quantity. You have a certain amount of energy, does not have a direction, right? So it's a scalar. So these sound very abstract, but I want to point out something to you, that the rate of change, right? So if you're just holding on to your momenta or your energy, you're obeying the laws of physics, nobody cares, nobody notices, right? But you are going to notice if it starts to change, right? Because it's not going to change on its own. You have to be interacting with an outside force in order to change a conserved quantity. And so those rates of change, right, if your linear momentum starts to go up all of a sudden, or your angular momentum goes down, or you lose or gain energy, that is going to be something that's really noticeable. And you can see here, these are words, these are like everyday words that people are saying like, oh, these are very important, right? The rate of change of linear momentum is force, right? This is the force from F equals ma. That's why force is an important concept, not because it's important on its own. It's important because it's the rate of change of a conserved quantity, right? Angular momentum, also kind of an abstract idea, but if you start to change your angular momentum, it is only because you are applying or having applied to you a rotational force called a torque, right? The rate of change of energy is what we call power, right? And a fourth conserved quantity, which I haven't included here, which you already know about from chemistry class, though, is like the charge, the negative charge on an electron, positive charge on the proton, that kind of charge is a conserved quantity also. And its rate of change is also something that is kind of more real, if you will, than charge, and that is current, right? So although the conserved quantities themselves are hard to define, hard to picture, and very abstract, charge, energy, and the momenta, the rate of change of them are everyday, very important terms in our lives, right? And we feel like we have a handle on those. So I think this is kind of philosophically interesting, right? Is that if you have a conserved quantity, it's not the amount, right? It's the rate of change. It's kind of like this. Like, it doesn't matter how far you are away from Boston. What you really care about is what the rate of change of that is. That would be your speed, Like this is just kind of like a general truism. All right, I'll stop going on about that. What about mass? So a lot of students will ask about this question. Why don't you add conservation of mass? Because you've been lied to date and told that mass is a conserved quantity, and that just simply isn't true. Okay, mass is actually just a proxy for energy, really. And so to the extent that energy transformations are very small, then it will appear to us that the mass is relatively unchanged. But if you actually go out to the 8th decimal place or something in a chemistry experiment, or if you think about like nuclear reactions, like the AMUs in different nuclei of different elements on the periodic table, you suddenly start running into the fact that mass is not a conserved quantity, and that mass is actually changing when you go from one nucleus to another, right? Why does the proton have a fixed mass in all the different type of nuclei. It's because a lot of the mass inside of individual atoms are coming from the relationship between the nuclei, one proton interacting with another proton or another neutron in there. And so it really is kind of an amazing thing, but over 90% of the mass, what you think of as a mass of a macroscopic object, actually comes from the internal energies inside of there, right? If you strip objects down to their fundamental particles, that is the electrons and the quarks that they're made out of, those things don't weigh anything. They weigh less than 10% if you add them all up, right? It's because they are pushing and shoving on each other and they're in motion, so they have kinetic energy and potential energies. And you add up all those energies, and that's actually where the mass comes from. So this most famous physics equation, E equals mc squared, that everybody can recite, hardly anybody really understands it. Yes, it explains where energy comes from in nuclear bombs and stuff like that, and that's usually where it comes up. But the more interesting thing is to kind of rewrite this equation in your head, like m is equal to E over c squared, right? That's actually that m, which is your mass, is coming from all of the internal energies inside of your body, all the microscopic kinetic and potential energies divided by the speed of light squared. That's what the c stands for. And that's where your macroscopic mass comes from. If you have a hot cup of coffee and you set it down and it cools down by 10 degrees, it's lost energy. It will weigh less, it won't weigh a lot less because the speed of light is such a big number. And so that's why it's okay under most situations to pretend that mass is a conserved quantity, but it really isn't. So I just want to point that out and also be able to fold E equals mc squared into the conversation. There's a second aspect to Amy Noether's work that she did in explaining the conserved quantities come from symmetries in the universe. And that ties in with another aspect of physics that overlaps with chemistry too. Of course, there's also all kinds of overlaps between the sciences. But this is the idea of the Heisenberg uncertainty principle, which generally comes up first when people are talking about electron orbitals, right? But is also just a general truism, right? That you cannot know precisely, usually what you're told, the precise position and the precise velocity at the same time. It's a little bit more complicated than that, but that's the basic idea. So anyway, what Amy Noether explained at the same time that she explained that symmetries drive conservation laws is the variable, the quantity that is symmetric is, and the quantity that is conserved is actually the pair of variables in a Heisenberg uncertainty principle. So a Heisenberg uncertainty principle is not just a trade-off between velocity and position for electrons in an atom. It's a generally true thing for all the conserved quantities. So for instance, because the universe is symmetric in with respect to position, there's a conserved quantity called linear momentum. And because the universe is symmetric in terms of what angle you're looking out into the universe and doing your science at, there's a conserved quantity called angular momentum. And because the universe is symmetric in time, there's a conserved quantity called energy. So these pairs of variables all obey the Heisenberg uncertainty principle. So Noether just kind of like proved that as an aside, that you have a fundamental trade-off between position and momentum. So you can see it's not really position and speed. It's the speed is inside of the momentum, right? Likewise, there's a trade-off between angle and angular momentum, right? If you want to locate a particle very precisely, you might have to give up on knowing its momentum. Same thing as if you want to figure out what angle a particle is at with respect to your measuring device, you might have to give up on some information about its angular momentum. Likewise, if you want to define very precisely what the energy of a system is, you may have to, you may not be able to do that very precisely in time, right? And so these are called conjugate pairs, and they all three obey the exact same Heisenberg uncertainty principle, which is respecting this idea in quantum mechanics that there's a granularity to the universe, right? You just can't keep going smaller and smaller. It's not infinitely regressive, that there are smallest nuggets of little kind of like areas, if you will, and that's defined by Planck's constant, which is an extremely small number, and that's why it doesn't affect us in everyday life. But when you get down there and start talking about things the size of atoms and stuff, you can no longer ignore this granularity. Kind of like if you're really far from a beach, you don't have to deal with the fact that it's made out of individual grains of sand, right? You just describe the whole thing as this, kind of solid structure that looks, as a beach. But then when you actually go on it and look at it very closely, then you have to deal with the fact that it's made out of all these tiny rocks. And so this is the general relationship for the Heisenberg uncertainty principle is you say the uncertainty in your measurement, your ability to measure a conserved quantity, times your uncertainty in being able to locate the object in the variable that drives the symmetry in the universe, right? The product of those two always have to be bigger than Planck's constant. Right, so here it is for angular momentum, and here it is for energy. Okay, so that was some crazy highfalutin ideas. Do you need to understand any of that or have any takeaways for a future test or something? I'll be honest and say the answer is no. But I hope you enjoyed sort of getting a taste of some of this, what I would call the beauty of physics. Okay, bye for now.